Hi everyone. So as you can see by the title, this is a some plants in a box, and people like to use these resistance soil um, moisture sensors, and then they eventually corrode and don't last very long. But now they have these new capacitive sensors, which everyone's talking about, which is basically a 555 um, that changes pulse with capacitance of the soil, which can be achieved pretty easily. So you can make your own one of those. Um, but as you can see with this, there are two wires, and it is buried in the soil. Excuse these plants. I just got these for free from someone who was just getting rid of them, and these are some offcuts of some green onions that I had, and some leeks. But basically, what I've done is I'm using still the classic resistance soil meter, but I didn't buy mine. I made my own using some spare copper-clad PCB, which I will show you, and just a few resistors. Now, what makes mine different from the commercial ones that you can buy that have like little op amp or just basically a resistor, a single resistor, is that I'm actually feeding the sensor using two analog pins, so A0 and A1. And on an Arduino Nano, you can have up to 4 sensors since there are 8 analog pins. And I'm also using two 100K resistors. Now, ignore all these other resistors, they're not connected to anything. So basically what I'm doing, instead of feeding like a positive signal, so like here's our V plus, and then we go through a resistor, and then our soil sensor probe, and another probe, and the other probe would be connected to ground, and then you would read with your ADC the middle pin, which is like your voltage divider. So what I'm doing here is I'm actually using two voltage dividers, but then I'm alternating which one grounds which. So let's say we have to read something, so we set this A12 pin high, and then that gives us our positive voltage so that we're not always using the sensor. It's only being triggered when we actually need to do soil reading. So it'll set both pins high. But then I'll set one of the either A0 or A1 low. So if I set A1 low, then we read our soil with A0. And then if I set A0 low, then we read the soil with A1. So basically it keeps swapping the polarity between the plates. So when, if you've done any like chemistry or you know how electrolysis works, then you would know that the copper likes to migrate depending on the current flow. So if we put it here, the copper would go from this terminal to this terminal, and then if we swap them around, it goes from this terminal to that one. So basically it's constantly switching every time we do a reading. Now I'm not switching it up really fast, I'm just switching it like here and then here. So in the code, right now I have it set to a delay of 3 hours, which is which I'm actually just delaying it for 1 hour 3 times. Just really simple. I'm not, this isn't final code or anything, but this soil sensor code is. So basically we have an array, because we're also averaging values. So we have an array, and then we set our pin mode. A0 is output, A1 is an input, and then we write A0 low, and then our A12 pin, or our 12 pin high. So that way we have like something like that. And then we do 5 readings of analog or of A1, and then we have our 5 samples, which will be this half of the numbers. And then we set A1 as an input. We write 12, or so, my bad. We set A0 as an input, A1 as an output. So it's the exact opposite of this. We don't have to write digital 12 high because it's still written high. And then we set A1 low, and then we do 5 more readings, and then we set A1 as an input so that it's back down to a high impedance state, and then we turn off pin 12 so that there's no longer any differential voltage across the probes. So that stops the corrosion completely. So in here we're corroding in one direction, and then in this part we're corroding in the other direction, so there's an equal amount of copper transfer between both pads. And then right here we're just averaging the sample, so we're summing all of the values inside of our 10 digit or a 10 number array, and then we're just dividing by 10 right here. So that gives us our average. Now, here's the output. And the resistors I got are from two separate packs. They're just average, regular 5% tolerance resistors. That's why the values here, the first 5 are pretty high, and then these ones are actually pretty low. It's because I'm using two different 100K resistors. If you match your resistors, they should all be pretty equal, but it actually doesn't really matter too much. We're not going for a high serious application. We're just, trying to make the longevity of our sensor pretty long, So here's our 10 values. You don't actually have to print these values. I just like to see. And then that's the average value, 93, 84, which means that the soil is pretty wet. I've estimated around 200. So any number below 200 is wet enough, maybe even 300, depending on your plant. But these plants like water, so yeah. So what are the advantages of using my sensor versus the commercial sensor? Well, with mine, there's no electronics on the board itself, so you can actually bury this. Most of the time, they're just poked into the top of the soil. My sensor is actually all the way at the bottom of this pot, so you can actually make sure that it's not just the top of the pot that you're watering. You can actually check all the way down.